Hello everyone, I'm presenting our work T3Time, Tri-Modal time series forecasting via adaptive multi-head alignment and residual fusion. Multivariate time series forecasting is critical for applications ranging from energy management to financial trading. While transformer-based models and LLMs have shown promises, current approaches face three fundamental limitations. The first one is modality-isolated architecture that emphasizes single representation. Then limited alignment capacity between multiple modalities. Finally, horizon rigidity with static processing across forecast lengths. These bottlenecks prevents models from capturing horizon-specific relationships in temporal data. So we propose T3Time, a novel tri-modal framework that addresses these challenges. We integrate three complementary modalities: time domain encoding for temporal dependencies, frequency domain encoding for periodic patterns, and finally LLM-based prompt encoding for semantic context. We integrate this representation using adaptive multi-head cross-modal alignment. We add horizon-aware gating and channel-wise residual fusion to make fusion adaptive and stable. Empirically, our model is consistently strong across benchmarks. This is our framework overview. We have a tri-modal encoding, then horizon-aware gating, then adaptive multi-head cross-modal alignment, and finally channel-wise residual fusion just before decoding. Let me walk you through our architecture one by one module. This is the first module. Here are three branches. We apply first Fourier transform to convert temporal data into the frequency domain. This is later processed through a transformer encoder to model spectral dependencies. Finally, we use learned attention weight pooling to aggregate frequency information. This captures global periodic patterns that are often difficult to detect in raw time series. The raw temporal signal is projected into latent space and processed via transformer encoding. These branches captures local temporal dynamics, trend information, and short-term dependencies that characterizes the time domain evolution of each variable. In the LLM prompt branch, we generate natural language descriptions of the input sequences, including time ranges, values, and trend summaries. A frozen GPT-2 model encodes these prompts, injecting rich semantic priors and domain knowledge into our representation speech. Each modality captures what the other misses. Frequency encoding is periodicity, time encoding is local patterns, and prompts provides contextual understanding. Together, they form a complete picture of the temporal dynamics. The next module, this module makes fusion horizon dependent. We learn a gate that adjusts the balance between temporal and spectral features based on the forecast horizon. So short horizon can learn more on the local time patterns, while the longer horizon can put more weight on the periodic or global structure. The next one is adaptive multi-head cross-modal alignment, that is CMA module. The module addresses a common limitation that was in prior architecture, that is a single alignment path through the CMA module can miss diverse fine-grained interactions. To address this, we employed multiple independent CMA heads. Each head computes cross-attention between fused temporal spectral feature and prompt embeddings. Then we apply a feature-aware gating network that dynamically weights each head's contribution rather than just averaging. This enables richer cross-modal interaction. The final one, just before decoding, we fuse the gated temporal spectral representation with cross-modal outputs using learnable per-channel coefficients. This allows fine-grained control over representation mixing. We compared T3Time on 7 widely used benchmark datasets, ETST, where there are 4 subsets: ETTM1, ETTM2, ETTH1, ETTH2, and ECL, weather, exchange, and ILI. These datasets' domains are electricity, weather, exchange rates, and illness. T3Time achieves state-of-the-art performance in 14 out of 16 baseline comparisons. Compared to the previous baselines, T3Time reduces MAC by 3.28% and MAE by 2.29% on average. T3Time demonstrates exceptional generalization. With only 5% data, T3Time reduces MAC by 4.13% and MAE by 1.91% compared to the previous state-of-the-art. With 10% data, improvements are 3.62% and 1.98% respectively in MAC and MAE. Our design analysis confirms each component's contribution. We experimented by removing 4 major design modules: frequency encoding, multi-head cross-modal alignment, channel-wise residual connection, and horizon-aware gating to assess the individual impact on model performance. The complete model achieves the state-of-the-art performance in most of the test cases. To validate our approach, we performed TSNE visualization across all embedding stages. Time series embeddings show clear dataset clustering with distinct separations, confirming our encoder captures dataset-specific temporal characteristics effectively. Frequency embeddings display distinct clustering patterns, demonstrating that our spatial branch successfully captures meaningful periodic structure. Prompt embeddings are most dispersed, reflecting the diverse semantic nature of our natural language descriptions. However, dataset groupings are still visible, showing that the LLM successfully encodes domain-specific context. For casted embeddings, this is crucial and shows smooth, coherent manifolds with circular or spiral structure. Unlike the more fragmented time and frequency embeddings, these final representations are unified and well organized. The progression from fragmented individual modalities to cohesive final embeddings visually confirms that our trimodal fusion works. T3Time does not just concentrate modalities, it harmonizes temporal, spectral, and semantic information into robust integrated representation. This explains our consistent performance improvements across all benchmarks. Thank you so much for your time and patience.